create a diode and what are the material properties of these diodes and so on. So this is basically discussed under the solid state physics, but this analog electronics is pretty much focused on analyzing a circuits containing diodes and whatever the electronic component. So to have this discussion, so we basically model the diodes. So then based on the model, we can explain the properties of the diode, or we can basically represent the actual diode with certain simple type of models, and we can replace this diode with these models, and then we can think of basically analyzing a circuit. Okay, so this is the entire idea of this discussion, and to make a kind of clarity, so I'll brief out what is actually a diode. So we know that from your A levels, we have this silicon or germanium substrate or a kind of a base. So we have silicon or a germanium base, and we include a kind of a atom, external atom called impurity. So impurity. So we brought a kind of alien type of atom and to this silicon base. So this is the this special atom called, it's a kind of an impurity. So this depending on the properties of the impurity, so we can basically generate two type of semiconductors. So one is this N type of semiconductor or N type. So the other one is this P type. So to have this N-type semiconductors, so what we can simply do is, so with the silicon base, so we can dope, or we can simply combine impurities, so which have 5 electrons, or so we can simply say that covalence electrons. So we can include this, so these valence electrons. In its last orbit. So we can basically bring a kind of impurity having 5 valence electron in its last orbit and mix it with this silicon material. So ultimately we have a kind of N-type material. So I believe like you have a kind of understanding about this generating or this implementing a kind of N-type material. Similarly, so we can have a kind of a impurity with 3 valence electrons. So in its last orbit. So if you mix these kind of impurities with the silicon or germanium substrate, so you can have a kind of a P-type material. So what happens is like, so if it is an N-type material, so with this doping of this impurity having these 5 electrons in this last orbit, what happens is we can have, so once you combine the silicon, which has the 4 electrons in its last orbit, with the 5 atom with the 5 electrons in its last orbit, what happens? We have kind of excess electrons remains in the material. So this rest of the 4 electrons are simply create a covalence bond with the silicon atom, and so we have free electrons in this material, so in this substrate. So in n-type material, so we have free electrons. So at the same time, if you basically consider these impurities we basically brought into this silicon or germanium base, so we can see those impurities basically create a kind of a donor type of atom. So this like, for example, if you think of a silicon plus a kind of a substrate impurity with 5 electrons in its last orbit, so we have free electrons. So at the same time, so then this whatever the electron of this impurity is now simply released to the silicon substrate. So then this impurity is having a kind of a ionic atom which has its proton level is higher than the electrons. Because for example, if you basically think of a kind of atom having 5 electrons in its last orbit, so what happens is, so these 4 electrons are simply combined with the silicon through a covalent bond, and this electron is simply moves out to the silicon substrate. So this is our free electron. So then this particular atom has protons which is higher than the electrons, because this whatever the electron here is released to the silicon substrate. So this electron is not anymore belongs to this particular atom. So this becomes a kind of a positively charged ion. So that's why, so in this n-type material, so we have free electrons and positively charged atoms. So similarly, you can think of an n-type material again. So in this n-type material, what happens is, so we have, p-type material. So we have silicon substrate. So, and we brought impurities which basically having this 3 valence electron in its last orbit. So, so then it's like if you have kind of atom with 3 electrons. So we have 3 electrons like this. And these 3 electrons are simply create covalence bond with silicon. And it basically create a vacuum for a 1 electron. So this vacuum is represented as a hole. So this vacuum means there's a kind of a void for an electron. So the if we consider the charge of this electron, so we can simply say that, so electrons have a charge of minus. So then we can represent this vacuum as a positively charged void. So then if it is a p-type material, so we can simply claim that, so we have holes. So I'm simply indicating these holes with these plus signs. So these are the holes. So in addition to these holes, we have certain set of ions having a negative charge. So we have ions with negative charge. So this is negative. So why it's negative actually? So whether we have a kind of a hole there, so the one electron from silicon, which is basically in this last orbit, is basically have basically linked to this impurity. So if you draw this covalence bond, so we have one from silicon. So there's a one from silicon, there's another one from silicon, but for this particular case, you don't have any uh, electron to create a kind of covalence bond. But so this electron from the silicon atom is basically sharing with this whatever the impurities you brought into this silicon base. So then the if you consider this particular atom, impurity atom, so this is actually having one electron higher than the whatever the protons in this particular atom. So then it's become a kind of a negatively charged. So we have one electron in addition to the protons we are having. So then, so if we make a kind of a simple summary, if it is an N type of material, so we can dope a kind of impurity having 5 valence electron in its last orbit with the silicon substrate. So ultimately, once you do this doping process, so we have free electrons in the material or the substrate, and in addition we have like positively charged atoms. So similarly we can create a p-type of material by introducing impurities with 3 valence electrons in its last orbit. So with this process, so we can basically have a p-type of material having holes in its substrate, and we have negatively charged atoms. So this you can basically control this number of free electrons or holes in this substrate by basically adjusting this doping level, or the how much you can uh, include this the concentration of these impurities will give a kind of an indication about the amount of free electrons or holes in this N or P type of semiconductor substrate. So this is the very simple idea about this N and P type of material. So any kind of question? So then we have P type of material. So P type. So for P type we have holes here. So we have holes. And in addition to that holes, we have negatively charged ions. So I believe like, so when I discuss with the students, we are coming from the link. So the issue is actually, so we have 2 sessions. So one is on Tuesdays and there's another session I couldn't remember, Wednesday or Thursday. So they basically split into 2 groups. So this is the group A is for telecommunication specialization. So the students who basically request telecommunication as their specialization, and the other session group B is for power and engineering management. So I'm delivering 2 sessions per week. I think so. All these materials are uploading to the LMS. So I'm basically covering the same content. Yeah. So I'll check with yeah. So see the session A or the group A and B. So group A is, if I remember, so group A is the telecom specialized students, or the student who request telecommunication as their specialization, and group B is like engineering, management, and power systems. So I'm basically doing the same content for group A and B. So I'll try my best to merge these two together, so then it's easy for me and you as well. So then I have a same content can be easily deliver to the same group. So at the moment you can see like all the sessions I'm uploading to this model, whether it's group A or group B, you can refer all these links. Okay. So then, so I'm referring this P-type material. So this is P-type. So in this P-type material, we have holes and we have negatively charged atoms. So this is our P-type material. So this P-type material, so the majority carriers are basically holes. So these holes are the one basically generating a kind of a current flow later on. So this is the N-type material. So this is N-type. So for this N-type material, so we have free electrons. So we have free electrons, and in addition, we have like positively charged atoms. So these are basically due to these impurities. So these impurities becomes kind of a positively charged atoms by releasing one electron to this material. So this is the N-type material and this is the P-type material. So once you basically connect these two together, so what happens is actually, so we have holes. So these holes are actually a kind of a void for electrons. So it's a kind of a space which easily can absorb a kind of electron. So this is the real physical nature of that hole. We assume that it's positively charged because it's a kind of a void of this electron. So it basically can immediately absorb a kind of a free electron from somewhere else. So that's why we assume that these holes are positively charged, because so this particular space or this void can basically accommodate a one electron. So that's why we assume that holes are kind of positively charged spaces. So once you simply join this P-type and N-type materials together, so what happens is actually, so these electrons or free electrons are simply combined with these holes. So once these free electrons are combined with these holes, what happens? So these holes are simply accompanied with these atoms. So the negatively and positively charged atoms. So this free electron is actually coming with this positively charged atom. So if you remember this crystal structure of this implementation of P and N-type material, so see, so if you create a hole, so it means a kind of a void for the electrons. So in this impurity we brought into the crystal structure of the silicon material, so this impurity become a kind of a negatively charged atom by sharing this one electron from the silicon. Similarly, so if it is N-type material, if you brought a kind of impurity having this additional electron from its last orbit, so it's create a kind of, it's release a one electron by combining the electrons of the silicon subatom with this having this covalent bonds, and then this whatever the impurity or the alien material atom you brought into the silicon as impurity become a kind of a positively charged by releasing this one electron. So then it means like if you create a kind of a one free electron, it automatically create a kind of a one positively charged atom. So if you create a kind of a hole in this p-type material, so along with that hole there's a kind of a one negatively charged atom appear there. So once you simply combine this p and n-type materials together, what happens is, so these free electrons are simply combined with these holes, and you basically create this kind of structure. So ultimately what happens is you basically create this kind of a structure. So here we have holes. So these are the holes, and at the same time you have these negatively charged atoms. So in this n-type material, so we have free electrons and positively charged atoms, impurity atoms. So once you just join these p and n-type materials together, so these free electrons are simply combined with the holes and create a kind of a region where you have this negatively charged ions are packed in this p side and positively charged ions are packed in n type. So without any biasing voltage, for biasing voltage means external voltage. So without having any external voltage, if you just join this p and n type materials together, so these free electrons are combined with the holes in the p side and create a kind of a layer here, which is actually kind of a neutralized region. So you don't have any free electrons or holes there. So then this is a kind of a, so you can model this as this kind of a capacitor having positively charged plate and a negatively charged plate. So then once you simply join this p and n layers together, you have a kind of a neutralized region due to this combination of these free electrons and holes. So this is called the depletion region. So due to this depletion region, once this scenario or the situation is stabilized, so then it basically create a kind of a neutralized region, so which avoid moving these free electrons from n layer to p layer furthermore. So after this pn or this combination of these free electrons and holes get stabilized, so it creates a kind of a depletion region. It's a kind of a neutralized region which avoid moving these free electrons across this region. So then due to this, it creates a kind of a voltage barrier. Voltage barrier. So we known as, so we denote this barrier voltage as VB. So in certain cases, we use this VK as a knee voltage. So either you can use a barrier voltage or a knee voltage. So whatever. So due to this depletion region, it creates a kind of a resistance to the movement of these free electrons across this depletion region. So this resistance can be simply demonstrate or model as a kind of a barrier for an electron. So the barrier for electrons can be represented as a kind of a voltage barrier. So it creates a kind of a voltage barrier across this p and n type materials, so which avoid moving free electrons across this region to the p side. So then what happens is, once you simply connect this p and n type together, So these free electrons are simply combined with the holes in the p layer and create a kind of neutralized region, which is known as a depletion region. So this depletion region create a kind of a barrier for these free electrons, and so then it's basically avoiding this movements of these free electrons across this depletion region to the other side or the p side. So once you simply connect this p and n-type material, so these free electrons are combined with these holes and create a depletion region which induce a kind of a barrier to the movement of these free electrons anymore. So this is the scenario happen once you connect this p-type material and n-type materials together. So let's see what happens if we apply a kind of a negative voltage across this circuit or this PN junction. So what happens? Okay, now, so we have P layer here and N layer here. So we connect an external source. So this is if you apply a kind of external source, it's known as a kind of a biasing voltage. So if you apply external bias or biasing voltage like this, so the way we connect this source is something like that. So here positive terminal of the source is simply connect to the N layer or the cathode of the diode terminal. So this is the symbol of this diode. So this is the cathode terminal of the diode or the N layer of the diode. So you can connect your negative terminal of the source to the P layer or the cathode of the diode. Sorry, anode of the diode. So the anode of the diode is simply representing the P layer and the cathode of the diode is representing the N layer. So this is the simple symbolic way of expressing a diode. So we have anode here and a cathode here. So this is anode and cathode. Anode represent the P layer and cathode represent the N layer. So if you basically apply negative voltage, so VD is negative. So VD is the voltage across the diode. So the subscript represent the diode. Voltage across the diode is negative. So the negative means, so this biasing voltage is reversed. Reverse voltage. How it becomes reversed is like you can have external source and plug its positive terminal to the N layer and negative terminals to the P layer. So this positive terminal to the N layer and negative terminals to the P layer. So once you connect in this fashion, so then the external voltage is applied across the diode in a reverse region. Okay, so then what happens? So we know that, so N layer basically having these free electrons and P layer we are having this holes there. So if you basically apply this kind of a potential across this PN junction, so what happens is due to this positive potential appear at the N layer, there's a huge tendency of combining these free electrons with these holes. Okay, so then what happens as shown in here, so this combining of these free electrons and holes is basically continuing and your depletion region is getting increased, or the width of the depletion region is getting increased and increased. So if you basically increase the supply voltage or the external voltage VD further and further, So it basically pushes all these electrons to the other regions to combine with the whatever the free electrons, and it will create a kind of a wider depletion region. Okay. So then once you increase this VD up to a certain level, so then this expansion of depletion region is not tolerable to this PN junction. Okay, so there is a kind of a particular voltage. So we'll basically denote it as a VPIV with a subscript of PIV. So this is peak inverse voltage. So peak inverse voltage. Okay. So this peak inverse voltage. So if you apply kind of a negative voltage or reverse voltage across this PN junction, and if you increase the value of this voltage, so once it's reaching to this peak inverse voltage, so then you can have a kind of a maximum width of this depletion region, and it's anymore cannot tolerated by the physical or the crystal arrangement of this PN junction. And if you basically increase the diode voltage beyond this peak inverse, so your diode is simply burn. So it's basically you cannot basically get a kind of a diode action anymore. So then it will not act as a kind of a diode. So if you want to keep this PN junction acting as a diode, so you have to basically apply a kind of a negative voltage less than this peak inverse voltage. So if you apply a negative voltage across the diode which is greater than this peak inverse voltage, so due to this negative voltage, this depletion region is getting increased and increased at this level. So then you can't see a kind of a diode action anymore. So it's act as a something else. So then so we can simply say that so it's not working or it's burned. Okay, so then if you apply kind of a negative voltage across the diode, so this would be the maximum voltage which this particular diode can manage, or which this particular diode can tolerate, is this peak inverse voltage. So if you basically add or increase the negative or the reverse voltage beyond that peak inverse voltage, so you can't see a kind of a diode action anymore. Okay. So this is what happens if you apply a negative voltage across the diode. So your depletion region gets increased and increased, and if your external reverse voltage is reaching to the peak inverse voltage, so your diode get collapsed. So then it's anymore act as a kind of a diode. So it becomes a kind of a material having this neutral charge. So it's basically simply a neutral layer. So you can't see any kind of a P and N layers. They are having a formal depletion region and act as a kind of diode if you simply increase your reverse voltage beyond peak inverse voltage. So this peak inverse voltage is the maximum reverse voltage that particular diode can basically manage or tolerate. Okay, so this is what happens if you apply a kind of a negative voltage across this diode. So we call this as a reverse bias scenario. Reverse bias. So this is called reverse bias scenario. So why it's get reverse bias? So we are basically applying external voltage. So this biasing voltage is the external voltage in a reverse fashion, or the negative voltage is applied across PN junctions. How it's become negative is like, so we are connecting the positive terminal of the source to the N layer and negative terminal of the source to the P layer. So this is the way we connect this PN junction to an external voltage. If you apply reverse voltage, so this diode becomes a reverse bias diode. So the other ways, like you can apply a positive voltage across the diode. So then what happens actually, if you apply a positive voltage across the diode, so see the way we connect the external source. So we have this positive polar terminal of the source is basically connecting to the P layer, and negative terminal of the source is connecting to the N layer. Okay, so it's completely different than the previous. So this is called forward bias. So this is forward bias. So once the diode is forward bias, mean your external source or the biasing voltage is connecting to the PN junction in this way. Plus terminal of the source is connecting to the P layer, and minus or the negative terminal of the source is connecting to the N layer. So we can argue in a similar fashion like in the previous case. So if you connect the external source in a reverse mode, so then this depletion region gets increased and increased. So if you basically apply a forward voltage, so this due to this potential arrangement, you can see that whatever the depletion regions appear there in the zero voltage across the diode is getting reduced. Okay, so the previous depletion region at this neutralized or the zero voltage scenario is simply reduced, or the width of this is simply reduced. So initially we have this width. So with this positive voltage across this, so this depletion region gets reduced, and it will basically create a kind of opportunity to move these free electrons from one side to the other side. So if you apply a forward bias voltage, what happens is, so the depletion region there in the PN junction is getting reduced, and it creates an opportunity to move these free electrons from one side to the other side. So this, due to this forward voltage, you can see a kind of a current flow through the diode. So the other scenarios, you don't see any current, but there is a kind of a very small current flow through the diode due to this minority carriers. But once you make this diode forward bias, you can see a kind of a current creates due to the majority carriers of this PN junctions. So it means like, so in the P side, these holes are contributing to this current, and in N side, so you have free electrons contributing to the current. So if basically, so these free electrons and holes of these layers, which are the majority carriers of these P and N layers, creates a current. So it becomes a current due to majority carriers. So this current due to majority carriers are in the range of milliamperes. If it is a kind of a current due to minority carriers, so that ID or the diode current is pretty much close to zero, and or else you can see a kind of a microampere range current. Okay, so then we basically identify few scenarios where we have positive voltages across the diode and the negative voltage across the diodes and so on. So what happens then, we based on this crystal structure and the behavior of the crystal structure, we can build the characteristic of this diode. So the characteristic of the diode means we are referring the voltage and current characteristics. So this voltage and current characteristics. So we are interested of this VI characteristic, or the voltage and current characteristics. So this is the VI characteristic of a general purpose diode. So this is basically operating on quadrant 1, first quadrant and third quadrant. So if it is a first quadrant, so where you have positive voltage appear across the diode, so we can simply claim that this is forward bias. So it's in the forward region. So this is forward bias because your VD is actually greater than 0. So when you apply a forward bias voltage by connecting your source, the positive terminal of the source to the P layer and negative terminal of the source to the N layer. So then this diode becomes forward bias, and with this positive voltage across the diode, you can see a kind of a milliampere range current. Again, like we know that. So this positive voltage is basically starting from 0. So if it is 0, we know that there is a kind of a depletion region appear in between this P and N layers due to this simple combination of these free electrons and holes. So then during this very first discussion, we found that with this depletion region, it basically create a kind of a barrier to these free electrons moving across this depletion region. So once you basically increase the voltage, positive voltage from 0, and if you slightly increase this, so we found that with this positive voltage, the potential drop or the barrier creates by this depletion region is getting lower and lower because the width of the depletion region is getting reduced. So with the reduction of this depletion region, there is a kind of a chance, or there's a kind of opportunity for these free electrons moving across this depletion region. So this, so if the voltage across the diode is basically equals to this knee voltage or the barrier voltage VB or V knee, whatever VK or VB. So this VB or V knee is basically representing the barrier voltage. So if we basically reduce this barrier voltage, or if you basically overcome this barrier voltage, we can see a kind of a current flow through the diode. So that's why if this diode voltage is basically move beyond this barrier voltage, so you can see a kind of a huge current flow through the diode. And again, it's operating the third quadrant as well. This third quadrant refers a negative voltage. So where you can see a kind of a reverse bias scenario. So once your diode is reverse bias, so we know that this depletion region gets wider and wider, and you can't see any kind of a current. But as we discussed previously, there may be a kind of a small current due to minority carriers. So the small current is simply visualized there. So this, you can see a very small current which is in microampere range. So due to this minority carriers, so this is known as a leakage current. So normally these leakage currents are created by these minority carriers. So this once this minority carriers creates this very small current, and at the same time, if you increase the reverse voltage up to the peak inverse voltage, so this is the peak inverse voltage, so this becomes the peak inverse voltage. Or in certain cases, it refers as reverse breakdown voltage, whatever. Reverse breakdown voltage or peak inverse voltage basically reflects the maximum reverse voltage which this particular diode can tolerate. So if you basically increase the negative voltage beyond that limit, so you can't see a kind of a diode action anymore. So then the diode get I mean, like, it's basically getting malfunctions. So these are the couple of parameters on this characteristic curve. So you should be basically aware about this parameter. One is this bias voltage. or in certain cases it's referred as knee voltage. For the silicon, it's like 0.7 volt, and germanium, it's like 0.3 volts. So these are known information there. And this, if he refers this VI or the diode characteristic of a real diode, so this diode is operating in both quadrant 1 and quadrant 3. During this first quadrant, so this diode become forward bias, because we are applying kind of positive voltage across the diode, and you can see a kind of a notable current flow across the diode. So once it moves to the third quadrant, where you are applying a negative or reverse voltage, so the diode get reverse bias, and the current flow is very small, which is in microampere range. And once you increase the reverse voltage, so then the diode get collapsed. So these are the couple of parameters or key elements which we basically wants to highlight in this discussion. So we have barrier voltage or knee voltage, and then peak inverse voltage, forward bias region, reverse bias region. Okay, so these are the few terms and notations we need to highlight. And at the same time, now we can summarize the entire operation of the diode by sticking into the characteristic curve. So these are the identified regions. VD is greater than or equal to 0. So we can split this into VD equals 0 case, VD, okay, sorry. So we'll do that. Okay, so we can split into VD greater than or equal scenario and VD less than 0 scenario. So we know that if this VD is greater than or equal to 0, so then ideally it should be forward bias. And once you apply a negative voltage, so the diode definitely would be reverse bias. So under this first scenario, VD is basically greater than 0. So we can split it into two sub scenarios. One is actually, so this VD is basically in between VB. So the applied voltage across the diode is less than VB. So the second is the voltage applied across the diode is greater than or equals VB. So the first case, again, whether this forward diode is forward biased by applying a positive voltage, so you can't see any current flow through this diode, 0. So if the voltage across the diode is greater than VB or equal VB, so you can see a kind of a current. And again, if you apply a negative voltage across the diode, you can't see a kind of a notable current. There's a current due to minority carriers, but so we'll simply ignore in this case. So we are basically focusing the current due to majority carriers only. So if you apply a kind of a negative voltage across the diode, again, you can't see a current. So then the diode current ID is 0. If your voltage is positive and less than the breakdown barrier voltage VB, so again you can't see a current. So if the voltage across the diode is greater than or equals VB, you can see a kind of a reasonably high current, which is in milliampere range. So this is the summary of this operational differences. due to different type of voltages. So the voltages appear across the diode is simply varying from minus infinity plus infinity. So this is the way that particular diode is operating. Okay, so then, so based on that, we can model the diode. So we know that we have a kind of a characteristic curve. So now it's up to us to model this diode. So the very first model is called the ideal model. So in this ideal diode model, what we can simply have is like, so in this model, we ignore the impact of this VB. So we avoid or we simply ignore this impact of VB. So then this VB can be assumed to be 0. So the easiest way to neglect or ignore the impact of the certain parameter is like by letting that parameter to be 0. So we did the same here. If you want to ignore the impact of this barrier voltage, you can simply let this VB to be 0. So then you can't see this region. So you can simply identify two regions, which is like VD greater than or equal 0. So then the diode gets forward path. So the second is like VD less than 0, diode get reverse path. So during this forward pass case, you can see a kind of a current. And in this case, you can't see any current. So it means if you apply voltage, it's on. If you apply negative voltage, means if it's like you're not applying any kind of a positive voltage, so it's off. So if you apply a positive voltage, so this becomes on. That's why you can see a current. If you apply negative voltage, so then this element is simply off. So you can't see any current. So this is so then this ideal diode model. So this diode acts as a kind of on-off switch. So then the characteristics of this ideal diode would be very similar to a normal switch. So it's something like that. Okay. So when you apply a voltage which is greater than or equal 0, so you can have a kind of a current. So this is forward region or forward bias region. So the diode is on. And if you apply a negative voltage across the diode, so this is referring this reverse bias region, and that is off. So then this diode acts as a kind of a switch. So if you apply a kind of a negative voltage, so switch is simply off. If you apply a forward voltage or positive voltage, switch is simply on. So this is on, this is off. Okay, so then if you basically stick into this ideal diode model, so we have two regions, so we can easily identify two operating regions. So these are the two operating regions. One is VD greater than C equals 0. So then during that region, diode gets forward bias. So the second region is VD less than 0. So then the diode is so if you are basically so you can simply replace the diode with a switch which is in off state. If you have a positive voltage across the diode when you are dealing with ideal diode model. So then you can simply replace the diode with a short circuit element or a kind of a switch which is in on state. Okay, so this is the simple model which we can easily obtain by neglecting the biasing voltage and whatever the nonlinear characteristic of this real diode. So we know that in the real diode characteristic we have nonlinear blocks and linear blocks and so on. So we avoid all these nonlinearities there and ignoring this barrier voltage effects as well. So then we can come up with a very simple sort of a model which is called as the ideal diode model. So where we can identify two main regions. If you apply a positive voltage, VD greater than or equal 0, so the diode becomes forward bias, and in that situation you can replace the diode with a short circuit element where your switch is in on state. So if your voltage across the diode is simply negative, less than 0, you can model the diode as an open circuit element, so which basically represent a switch which is in off state. So then simply for the ideal diode model, so for the ideal diode model, we can simply identify two regions, VD greater than or equal 0, then the diode is in forward bias region and diode can be replaced as a short circuit element. Or switch in on state. So the second operating region is VD less than 0, can be simply identified as a reverse region. So it's like open circuit model. And can be replaced it with a switch which is in off state. Okay, so this is the first very simple model which is called ideal model. Two regions, and during these two regions you can either replace the diode with a short circuit element or a kind of open circuit element. Okay, so then we move to so we'll try to accommodate few more. So this is a kind of an ideal diode. So the ideal diode is simply working as a kind of a simple switch. So the next is actually a simplified model. Simplified model. So in the simplified model, so we'll basically treat this VB as well. So we'll bring this impact of this VB as well. So then we can identify three regions like in the previous. VD greater than or equal 0 when VD is less than or less than VB. If the diode voltage is between 0 and the barrier voltage, so you can't see any current, ID equals 0. Okay. So then the second subphase, VD is basically greater than or equals to VB. So then you can see a kind of a current flow through the diode. So then this becomes on. That is on. So the other operating region is VD is less than 0. So then you can't see any current. Okay. So this is basically off. If you don't see any current, so this diode is simply off. If you see a current, so then that is simply off. So if you want to model these characteristics, so you can see this kind of a characteristics. So you can simply see this kind of a characteristics. See, like, can we basically highlight these three regions? So this basically refers VD less than 0, and this block is basically referring VD less than VB and greater than 0. So I'm referring this block. So then this third is actually VT greater than or equals VB. So if the voltage across the diode is greater than or equals VB, you can see a kind of a current flow through this one. So then it means, so this unit is simply on. So otherwise during this region, so the device is simply off. So then this is the characteristics. Okay, so this is actually the shifted version of, so this is actually shifted version of the ideal diode. So the ideal diode is something like that. So the ideal diode is this. So if you shift this ideal diode's characteristic by VB to the right hand side, so you can have this kind of characteristics. Okay. So then, if you want to basically replace the diode when we are basically sticking into this simplified model, so if you want to replace the diode when you apply a positive voltage, so you have to replace this diode with this arrangement. So you have fixed source and an ideal diode. So this is ideal diode. And this is a fixed source of VB. So this fixed DC source representing the barrier voltage. So this is representing the voltage or the barrier voltage. So this represents the barrier voltage. So if it is forward bias, or if, for example, if you apply a positive voltage greater than or equal 0, so you can identify two sub-regions where your positive voltage is less than the barrier voltage. You can't see a current, but the voltage is greater than the barrier voltage. You can see a kind of a current flow through the diode. So then during this forward bias scenario, you can simply replace the diode with this model, ideal diode, and a series fixed DC source of VB. So VB is representing the barrier voltage. So if it is a silicon, so it's this VB equals 0.7. If it is a germanium type of a diode, so this becomes 0.3. So this is actually the diode. So this is the actual diode. Okay. So the actual diode, is simply replaced during this forward bias region with the ideal diode and a series fixed DC source of VB. So keep in mind, so this is the actual diode. So if you we basically replace this actual diode in the circuit with this block. Okay. So this circuit block basically represents the same operating scenarios. For example, this is ideal diode. So to make this ideal diode conductive or to make it on, so you have to apply a voltage across these two terminals. So which is actually greater than 0. So if you apply a voltage across these two terminals, which is greater than or equal 0, so this ideal diode gets on. Okay. So then if you think of this, so now these are the two nodes of the original diode. So this is node A, this is node B, so this is node A, this is node B. So I'm replacing this real diode, which is connected in between node A and node B with this ideal diode plus a series voltage source. So now the first scenario, your VD is less than VB. So then what happens? So the voltage across these two terminals yes. So in this circuit, so we can't simply differentiate whether the diode is ideal or a simplified one. So what we simply do here is we have a circuit containing diodes. To analyze the circuit, so we either stick into the ideal diode model or a kind of a simplified diode model. So if you basically stick into either one form, so then you can replace the diode depending on the operation. So we'll see one example. So then you can basically have a kind of idea how we apply these two models in a circuit to analyze a circuit. So until then, just wait and see. So these concepts. So later on, we'll discuss one example. So then you can see how we can analyze the circuit by applying ideal diode model and simplified diode model. Okay. Okay, so now we are basically applying a voltage across these two node A and B, which is a kind of a positive but less than VB. So then the voltage across VAB is, so VAB is actually less than VB. So then it means, so see what happens, what about the voltage across this diode? So how do you evaluate the voltage across the diode is this. So we'll have next one. So this is the original replacement. So this is A, B. So this is the actual diode is simply across A and B. So now we replace it with a simplified model. And we have a fixed DC source of VB. Okay, so this is the ideal diode. Okay, so this is the ideal diode. So we know that if it is ideal diode, if you apply a voltage across this ideal diode, so let's say that VDI is greater than 0, so this becomes forward bias and OR. If this voltage across this ideal diode is less than 0, so it's simply reverse bias and off. Okay, so let's have this. We'll apply VAB, a voltage across this A and B terminal. So which is the voltage across this actual diode. So the voltage drop across this actual diode, VAB. In between 0 and VB. Okay, so see then what happens to the diode. Okay, so if you want to evaluate the voltage across the diode, evaluate the voltage across the diode. How do we do is actually first remove the diode from the circuit and keep it open. Keep it open. Then evaluate open circuit voltage across these two nodes. So first we remove the diode from the rest of the circuit and keep it open. So then we'll evaluate the open circuit voltage across these two nodes. So then this V open circuit voltage. So V open circuit, V open circuit is actually voltage across that. So this is the applied voltage across diode. So if you want to find the actual voltage across the diode, what we can simply do is remove the diode first from the circuit and keep that open and evaluate the open circuit voltage across these two nodes. So which gives the actual voltage applied across the diode. See, now we need to find the voltage across the ideal diode. We know that if you apply a voltage across ideal diode which is greater than or equal 0, so then the diode gets on and you can simply replace it with short circuit. So this is replaced with a short circuit element. If you apply a reverse voltage or voltage less than 0, so it with the open circuit element. So see what happens when the voltage apply across A and B is in between 0 and the barrier voltage. So VAB is actually in between 0 and VB. So we'll remove that first to open. Okay, so we had a diode there like this, and we remove it from the circuit and keep it open and evaluate the open. So this is the negative of the diode and this is positive terminal of the voltage. This is the open circuit voltage across two nodes as out there in the previous scenario. So we first and keep that open circuit voltage across the diode. So when you are circuit voltage, so you know the orientation of the mark these two terminals plus and minus based on the cathode would be negative and anode would be positive. Mark the polarities of this open like this. So this becomes minus, this becomes plus. Voltage across this actual diode V. Let's assume this is VB and this is minus. Search of voltage low for this C like VOC voltage plus V like so this is VA So then VOC equal okay. If is less than VB, VOC is simply negative. So whatever the quantity happy in the VAB, VOC is simply less than 0. And so if it is off, you can with the show open circuit element. Okay, so this block 0 and VB, so the circuit is okay. So the ideal diode. So to this open circuit scenario, it element go through the device. Okay, the diode, so it's like 0. If you connect, so it's 0. So similarly, so next think of, so if you apply voltage VAB is greater than OC to AB minus VB and E. So VOC would be this greater than 0. So then the I the and claim that it is on. During this flow, you can see the dot is greater than or equal to the source of VB and short circuit element. So voltage across the dot when the voltage of VB. Why it's so? It gives the voltage. Okay, so it means like voltage across the dot is voltage of VB across the diode. So you can again see and simplify. So this third case, VAB is less than 0. Yes, actually my internet is not stable. I am connecting to we don't have power there. So anyway, this LMS, I believe like you can manage. So once the voltage across the A and less than zero, search of voltage low. Here we have. So this is VA. So then VOC plus VAB. Apply Kirchhoff voltage law. So then from this we plus VB. So it's minus of VB plus VAB. So this is always negative. So then we can simply claim that VOC is the voltage across the ideal diode, which is less than zero, means this diode is reverse bias and can replace with open circuit element. Kind of a simplification. Okay, so this is done. Okay, so we'll go to one example. So then you can. So I'm referring the exercise 1 in the slide set. So here you have to find these parameters like voltage across the diode VD. So then the current flow through the diode ID. Okay. So how do you do this? Okay. So let's stick into the first model. So let's assume like it's not here for the time being. So then you don't have any idea about the material. So then we can basically stick into the very first model, ideal diode model. So ideal diode model, which is greater than or equal to 0. So this is forward bias and can be replaced with the short circuit element. If it is less than 0, this is reverse bias and replaced with open circuit element. So this is the very simple regions of this ideal diode model. So we'll stick into this ideal diode model as ideal diode model. So first we need to find out the voltage across the diode. So how do you find it out? First replace the diode from the circuit. And mark the terminals according to the orientation of the diode. So this becomes minus and this becomes plus. So this is the open circuit voltage. So now if you basically evaluate the open circuit voltage across these two terminals, it gives the exact voltage appear across the diode. See, so now this is open, means there won't be any current flow through the network. So the current flow is simply 0. I is 0. So there won't be any voltage drop induced across this 2.2 kilo ohm resistor because no current is remove this diode and make it open. So then if you apply Kirchhoff voltage law, VOC equals 8 volt. So there won't be any drop introduced by this 2.2K because no current flow there. So the voltage drop across this open terminal is simply equals to this source voltage. So from this we can claim that open circuit voltage is greater than 0. So the VOC is actually the voltage across the diode. So this is equals to VOC, which is greater than 0. In this case, it's equals to 8. So this is equals to 8 volt and greater than 0. So based on the ideal diode model, then we can claim that if the voltage across the diode is greater than or equal 0, so this diode is definitely in forward pass. So this diode is forward pass now, and you can replace the diode with a short circuit element to simplify the circuit. So now you can replace the circuit with a short circuit element. For the evaluation analysis purpose. So you replace the diode with the short circuit model. Now you can evaluate these values. So what about VD? Voltage drop across the diode. So it's simply 0 because it's short circuit. Why it's 0? So this diode is simply replaced with short circuit element. So then there won't be any drop across the diode. So that's why it's 0. So what about ID? ID equals actually 8 volts. So this is the total voltage. And if you divide by the 2.2K resistor, so it gives the diode voltage. And what about the voltage across the resistor VR? So the entire voltage delivered by the source is applied across the resistor because now this diode acts as a kind of a short circuit element. So VR voltage drop across the resistor is simply 8 volt. Okay. So did you got the point? If you stick into the ideal diode model. So, okay. So let's think of now what happens if it is a simplified version. So the second is like we'll stick into simplified model. Okay. Again, so the voltage across the diode, the evaluation of the actual voltage across the diode is very simple, whether it's ideal or simplified. So you can simply follow the same technique. Open it and evaluate the open circuit voltage. In this case also, we can simply claim that open circuit voltage is actually 8 volt. And this is the diode voltage actually, which is greater than 0. So then if we stick into the ideal diode simplified model, we know that if the voltage is greater than 0, and if it is the silicon diode, okay, if we are simply dealing with VB of 0.7 for the time being, assuming that this is a silicon diode, so then we can replace this diode with this model. Now, instead of this short circuit element, we have a source of 0.7 volt and a kind of ideal diode here. So the voltage across the diode is greater than 0. So this ideal diode can be simply replaced with the short circuit element. So now I'm taking to simplified diode model and replace the diode with 0.7 fixed DC source plus a short side voltage appear across this diode is basically 8 volt. So we know that this is 8 volt. So it's greater than VB. So this is again greater than VB because this is 8 volt greater than VB, and we can simply replace this diode with this model. Source DC source of 0.7 volt plus a kind of a short circuit element. So this is the replacement. So then we'll try to find the parameters. Now this is the actual diode. So this is the diode. So what about the voltage across the diode? So in this case, if you may place a kind of a voltmeter across these two terminals A and B, so what is the actual value of this voltmeter? It's 0.7. So this voltage drop across the diode is 0.7 volt. Because it simply measures the voltage across the DC source of 0.7. What about ID? Current flow through the circuit. So if you apply Kirchhoff voltage law, so we know that the net voltage drop across this resistor would be 8 minus 0.7. So here, so you have a kind of this, and here you have a drop like this. If you basically mark the polarities or the voltage drop across the resistor by considering the direction of the current flow, as this is plus and this is minus, so you can simply claim that VR, voltage drop across the resistor, equals VR is actually 8 minus 0.7. So this is like 7.3 volt is the voltage across the resistor, and if you simply divide this 7.3 volt by 2.2K, so it gives the current flow through the network. Okay, got the point? Oh, is there any questions? So if you have questions regarding this, you can see. Let me know. Okay, so seems not. So we'll move to another example. Okay. So you have this circuit. And you are asked to find the V out. Find V out. So V out is the voltage across the resistor. So this is V out. So your input is a kind of a sinusoid like this. So you have a diode here. Okay. So you are asked to evaluate the voltage across the diode. Okay. So how do we do this? So by looking at this, we can simply say that your input voltage has two polarities, two phases. So you have first half cycle is positive and the second half cycle is negative. Okay. So it means like during this first half cycle, so this is plus and minus. So once it comes to the second half cycle, so this become minus and this become plus. So that's why you indicate these two voltage just as pluses and minus. Okay. Okay. Yeah. So we can basically represent this input Vi like this, Vm sine omega t. So this is your input. So now our target is to generate the output across the resistance R when the input is Vm sine omega t and having a seriously connected diode. So how do you do that? So first we need to identify whether this diode is forward or reverse based on the applied voltage. So we are applying a voltage of Vi, which is behave as a Vm sine omega t, and we need to find out whether the diode is forward bias or reverse bias based on the applied voltage. So how do we do it actually? So first find out the voltage, actual voltage appear across the diode. How do you do it? So first remove the diode and make it open and apply Kirchhoff voltage law and find out the open circuit voltage. So according to the orientation of the diode, so this is minus and this is plus. So this is the open circuit voltage, VOC. And this is your input voltage Vi equals Vm sine omega t. So once you remove this diode and make it open, so you can't see any current flow through this network. I is actually 0. So then there won't be any voltage drop across this resistor. Let's assume this. For this case, V out is 0, no voltage across the resistor. So then, by applying Kirchhoff law, we can simply claim that open circuit voltage equals Vm sine omega t, isn't it? So this is Vm sine omega t. So this is VOC. So VOC equals Vm sine omega t. So this is the voltage across the diode. Voltage across the diode is the open circuit voltage at this level, and which is equals to Vm sine omega t. So this is the simple observation we can easily made out of this circuit. So the actual voltage appear across the diode is exactly similar to the input voltage. Actual voltage across the diode is exactly matching with the input voltage. So then we can say that the operation of the diode is simply depend on Vm sine omega t. So then the next point is to analyze this circuit, either we can stick into the ideal diode model or simplified model. So first we stick into the ideal diode model. So ideal diode model is assumed. So for the ideal diode model, we know that we can easily find two operating regions where the diode is greater than or equal 0. This is forward bias and can be replaced with short circuit. If it is less than 0, this is reverse bias and replaced with open. So these are the two regions of the ideal diode model. So we assume that so this diode is basically behave as ideal diode model to analyze the circuit. Now this real diode is simply replaced with the ideal diode model. So that's why we made this assumption here. So without these assumptions, whatever the calculations or the analysis you carry forward here is simply invalid because everything depends on this assumption. So you have to clearly state these assumptions, otherwise your analysis is completely wrong and invalid. Okay, keep in mind, without this assumption, so you can't move forward. Either it should be stated in the question paper, or else if not, you have to specify it here clearly. Otherwise, the analysis afterward is completely illogical. Okay, so we first stick into the ideal diode model. So the identify two regions. If the voltage is greater than 0, so you can simply say that diode is forward. If the voltage is negative, you can simply say that the diode is reverse. So we know that the voltage drop across the diode is simply following the input. So see that what happens. So this is T. So this is Vm sine omega t. So this is Vm sine omega t. According to our analysis, we found that, so this is the voltage across the diode. So during this block, during this half cycle, Vd is greater than or equals 0, isn't it? At these 2 points, your Vd is simply 0. So otherwise, the voltage across the diode is simply greater than 0. So then during this block, this half cycle, diode should be forward biased because you are applying a voltage like this. So during this block, Vd is greater than or equal 0, diode is forward biased. You can replace it with short circuit element. Okay, from A to B. From B to C, we can simply say that the voltage applied across the diode is negative. So during this block, voltage is reversed. So this Vd is less than 0. And that should be definitely reverse bias. Yes. So during the second half cycle, voltage applied across the diode is simply less than 0. Then the diode is reverse bias, and you can simply replace the diode with open circuit. Okay. So we first found the actual voltage across the diode. So then based on that, we can basically identify whether the diode is forward or reverse depending on the voltage across the diode. So then we stick into either ideal diode model or simplified model and then do the analysis. For this particular scenario, we thought of synchronizing first with ideal diode model, and we assume that the actual diode is now behave as an ideal diode. So then based on the voltage across the diode, we identify what are the regions where the voltage drop across the diode is greater than or equal to 0 and less than equal to 0. Greater than or equal to 0 and less than 0. So based on that, we can simply identify whether the diode is forward or reverse. If the diode is forward, for the diode ideal model, we know that diode can be replaced with short circuit. If it is reverse, you can replace it with open circuit. Okay. Now we'll find the outputs. So the outputs depends on the mode of the operation of the diode, whether the diode is forward or reverse. So we'll see. When diode is forward bias, what about V out? So then the circuit is something like that. So this is short circuit. You have R, you have Vi, which is equals to Vm sine omega t. So this is plus minus. What about V out in this case? V out is exactly equals to Vm sine omega t. Because this diode is now replaced with the short circuit element and you don't see any diode there. You have a resistor in parallel with the source, and the voltage across this resistor is simply the value of the voltage. So the V out is Vm sine omega t. So the second, what happens when it is reversed? Because we know that during this positive cycle, so diode get forward bias. During this negative cycle, diode get reverse bias. So then again, the reverse likewise. So then we can simply analyze the operation of the circuit for the forward region and reverse region separately. So then we can simply give a kind of idea about the output V out. So for this case, So you can replace the dart with open circuit element because it's reverse. So here you have input voltage Vi. So this is your output. So for this, what about V out? So V out is simply 0 because it's open, and this source voltage is simply isolate from the resistor. So whether you have a source, due to this discontinuity here, you can't simply apply this whatever the Vi across the resistor. So the output voltage or the induced voltage across the resistor is 0. If the diode is forward pass, this is the output voltage. If it is reverse, this is the input voltage. Okay. Now, so we'll draw the output on top of the input. So this black line represents the input, which is again equals to the diode voltage as well. So then output would be during this forward bias region. So your output is exactly equals to Vm sine omega. So this is Vm sine omega. So during the reverse region, your output is 0. Okay, so this is your V out. Okay, so it means like during this positive cycle, you have this block, and during this negative cycle, you have 0 volt. So this is your output. So this was discussed previously as the half wave rectified version. So this is like half wave rectification. Okay, so once you apply this ideal diode model, you can see this kind of a negatively clipped signal. So you don't see the negative half cycle of the input signal. You can have this positive half cycles on. So it's like this. So this is the voltage drop across the resistor. Okay. So it's very simple. So next time, so come up with the output if you assume that diode is following simplified model. Okay. So just try at this second. So the circuit is very similar. So nothing else. So you have the same circuit. So you have this circuit. So this is your circuit. And try to draw the output when this diode is following simplified model. So see what's the real difference between the ideal scenario and the simplified scenario. So we'll discuss it next time. So what happens to the output when it is simplified, following the simplified model. Okay, and other than that, I want to see this. Yes, so okay, hope you can see this one. Yes or not? Can you see the screen? So I'm sharing a different version. Yes, so this is actually, so this is multisim live. So you can find out this from this National Instruments website. So if you basically search multisim in National Instruments, you can see this one. So this is actually very user-friendly interface. You can simply trial out this different type of circuits. Okay, so for example, you can see this in the left hand side, you have this toolbox. So you have different type of thing arrangement. So you have different type of sources. You have different type of resistors and so on. See, like you have different type of. So you have diodes. So all are there, diodes, NS, LED, general purpose diodes, and so on. Then operational amplifiers, resistors, capacitors, inductors, potentiometers, fuse, transformers, whatever. Then different type of sources, AC, DC, clocks, triangular waveforms, all kind of. So then you can have this analysis and annotation tools. You can measure the voltage, current, digital outputs. You can set the reference and so on. So, and transistors as well. So you have different type of transistors also. So this is a kind of ideal platform to just to simulate it, what happens to the circuit and see. So here you can put the schematic diagram here. And once you select the split mode, you can basically have these two windows separately. So you have this schematic diagram in the left hand side, and you can see the output waveform of this V1 and V2. They are in the right hand side. So at this right hand side corner, you can basically change the configuration or the parameters of different elements and sources. And once you basically put the, so here this, if you set it to transient, you can see the results for the transient scenario. Okay, so this is a one very simple tool you can basically try out, because from this onwards you can have different type of diode circuits. So you can see what would be the output for those kind of circuits by simply simulating it here. So this is called multi-sim live. So you can simplify it from National Instruments website. You can Google it as multi-sim live. So you can just put your email address and register there. So it's a kind of a free online tool. So you can then register there and load it this multi-sim live. You can create the schematic diagrams here, and you can see what would be the output for this. So this is a very simple tool. You can visualize those results, because we don't have any lab sessions there in physically. So if it is a kind of a lab, you can basically wire these circuits and get a kind of understanding about the output and change the parameters and see what happens to the circuit. But now with this COVID, you can't do it. So this is one way of basically getting an understanding about what could be the outputs and so on. So this is a simple tool. You can test it out. What are the outputs for different type of circuits? So you can try it out. So later on, I'll planning to introduce few assignments related to MATLAB. So then you can try out some coding in MATLAB. So, and at the same time, we thought of introducing a kind of a crash course of MATLAB. So you can follow it through the module and learn by yourself and try to do something. Yes. Yeah, you can just Google, search it on Google. So this is called Multisim Live. Multisim Live. So it's Multisim Live. So you just search it, so you can find it. Okay. So for the today, so we'll wind up the session, and if you have any questions, so you can bring it to the next sessions. Okay. So one requested to go through the previous example again, so we'll do it next time. Okay. Okay, thanks.